inverse Laplace transforms. For this, we're trying to get from the function of s to the function of time. And to do that, we perform the inverse Laplace transformation of the function of s. I'll demonstrate this with 2 questions and a quick run through, before giving you a chance to have a go yourself. Find the inverse Laplace transform of s over s squared plus 16. Now we've got the function of t on the left hand side in the table, and the function of s on the right hand side in this table. So we're going to start off by looking at the right hand side and comparing it against this equation we've been given. If we look down the list, it seems to most closely resemble this one here. So our function of t will be cos at u of t. We've only got one constant that we need to pull out from this, which in this case is a. Now we can see everything in this is the same as this, with the exception of this a squared. So we need to figure out what a is. Well, we can do that by, well, if 16 is a squared, a must be the square root of 16. So I'll just write on the side a equals 4. Now if it helps you, you can rewrite this inverse Laplace transform of s over s squared plus 4 squared. And we can use the table which f of t states that it must be cos of at, or 4t, because a is 4, multiplied by the unit step function. And there we have it, f of t equals this. Second example now, we've got this question. If we have a look down the table, we've got 2 options. We've got this one and this one. The difference being is this sign here. Because it's positive, we must be using this one. We can see b at the top, which is 7, and 7 squared is 49. So that's easy enough for us to state that b equals 7. For our a value, we've got in the table that it says minus a here, but positive a here. So where this is a negative, a will actually become positive. So we have minus 6 here, therefore a must be positive 6. Inputting this into our f of t expression, we then have f of t equals e to the at, or 6t, multiplied by sine of bt, or 7t, all multiplied by the unit step function. First set of questions for you to have a go with. Pause the video and resume when you're ready for the answers. Here the answers are in all their glory, so let's move on to the next part, which gets trickier. Now we're dealing with expressions that don't quite conform to these f of s expressions. If we start off by checking which of these table functions we need to use, we can clearly see that it must be this one here. So the first thing I'm going to do is write out this in this format, assuming we've not got any variations. I'm first going to write this nicer, so we have this a squared in an a squared format. So we have the inverse Laplace transform of 15 over s squared plus 5 squared. Now as you can see here, this 15 doesn't quite conform to this, because this is meant to be 5. Much like in integration, you can actually take out a numerical factor, so that numerical factor can be pulled out and multiplied on the outside. To do this in a nice way that's consistent across equations and questions, we currently have 15, and that's going to be equal to 2 factors. The first of which is the factor we want, which is 5, as we want 5 in the numerator. It's being multiplied by something else. Now this one's quite obvious because we can clearly see that 15 equals 5 times 3. So we can replace that numerator with the inverse Laplace, 5 times 3 over s squared plus 5 squared. And because we want to take out a numerical factor, we want to leave in this 5, but take out this 3. So we'll actually have 3 lots of the inverse Laplace of 5 over s squared plus 5 squared. And now at this point, it conforms with this f of s expression. So all we have to do now is find the inverse Laplace of this, and that will be multiplied by 3. So we have a, which equals 5, and we'll have 3 lots of sine of 80, or 5t, multiplied by the unit step function. And there is our answer. We'll have one more go with a trickier question, and then we'll have the second set of questions for you to try. we've got the function of s equals all of this, determine f of t. We're going to perform the inverse Laplace transformation of what's in the curly brackets. Like with normal Laplace, you can break things down into separate elements. Focusing on the green side first, notice in the table we haven't got a coefficient of this s squared value, so we're going to have to take out a factor of the coefficient in the denominator, which in this case is 5, so we'll take out a factor of a fifth from this inverse Laplace transformation, which will leave us a fifth of the inverse Laplace of 6 over s squared minus 9. We then have this 9 value to deal with, which as you can see, 9 is equal to a squared, so therefore a must be 3. So we've now got a fifth of the inverse Laplace transformation of 6 over s squared minus 3 squared. Now we need to deal with this numerator. As the table says this numerator should be 3, we need to take out a factor that would leave us with 3 in the numerator. 2 multiplied by 3 equals 6, so we'll take out a factor of 2, leaving us with 2/5 of the inverse Laplace transformation of 3 over s squared minus 3 squared. Now we've got this in a format we can perform an inverse Laplace transformation for. We can go ahead and do that, and that will leave us as 2/5 of sine h of 3t. Performing the same process with this blue side, we can see we want to deal with this power of 5, as this is actually n plus 1. So let's rewrite this as the inverse Laplace of 2 over s minus 3 to the power of 4 plus 1. So we can pull out the information that 4 is our value of n. That means the numerator is 4 factorial, which equals 24. However, the numerator isn't 24 as we can see, it's 2. So we need to take out a factor that multiplies to 24 to leave us with 2, or 24 times something equals 2. I would actually find a 12 multiplied by 24 would give us 2. So we can take out a factor of a 12th to leave us with what we need. We've now got this in a form where we can perform the inverse Laplace transformation. The last value I want to pull out though is the value of a. In this case, it's just going to be 3. Now this we could have pulled out all the way from the start. Putting this into our function of t, this would be a 12th of e to the 3t multiplied by t to the power 4. You can also write this of a 12th of t to the power 4 multiplied by e to the power 3t. We've then got the final answer of the function of t, and all of this is multiplied by the unit step function. Here's the second set of questions. As usual, they get trickier as they go along. Pause the video and resume when you're ready for the answers. I hope you did really well. Remember, the fully written out answers are on my website at letsdomaths.co.uk. The next video continues with inverse Laplace transforms, focusing on the completing the square skill. Stay safe and healthy out there, and I'll see you in the next video.